Okay, Shabab. Today I'm going to explain imperfection in solids, part number 2. Just to continue what we studied last week. What is the issue to be addressed today? Just reminding you, we study the imperfection in solids, and we say there is no perfect material. Supposed to be imperfection is there. We study the point defects. The point defects, this means we know this is a vacancy, sometimes interstitial or substitutional solid solution. Okay. Today I'm going to explain linear defects. It's called dislocations, planar defects, and bulk or volume defects. Let me go ahead here. Shabab, are you listening or hearing me? Is that clear?
Yes.
Okay. So linear defects, or called dislocation, is very important to understand the word, because as I told you from the beginning, material science has many terminology. You're supposed to know at least most of them. Okay. Are one-dimensional defects. If you remember, in vacancy or point defects, we have one atoms, not only one atom. Billions of atoms are missing in their place. This is called point defect. But if I have a line of missing atoms, this line is called dislocation. Okay. One-dimensional defects lead to the atom misalignment. If you look at here, I think this is 3D image of the arrangement of the atoms. As you've seen it here, this is a continuous lines, as you've seen it. But here in that place, there is a missing. Supposed to be continue like this, but is not continue because there is missing lines of atoms in this place. Okay, that is called linear defects. This causes slip between the crystal planes when they move. I will explain this part in details today. Produce a permanent plastic deformation. I think starting from maybe 2 more weeks, you will understand the difference between elastic and plastic deformation. Dislocation types, we have 3 types of dislocation. The first one is called edge dislocation. The second one is screw dislocation. And the third one is mixed. Most of them, of course, is mixed, but you have to understand the edge and screw. Let me go ahead to linear dislocation. If you look at here, I will give you some graph to let you understand. The linear defects is commonly designed by inverted T. This is very important to understand that symbol. Symbol is called inverted T, which represents the edge of an extra half plane of atom. Okay, look at here as well. Do you see this graph? This 3D image graph, like the graph I presented in last just the previous slide. You see, this is like T. شايفين يا شباب? Inverted T. Do you see it, شباب? Have you figured out?
Yes.
Yes. You figure out this is called inverted T, as you've seen it here. Suppose if this is a perfect crystal as this part, supposed to be continue like this, it will be atoms here, right? But missing atoms here and make inverted T. This inverted T is called linear defects, okay? Or sometimes it's called dislocation. Distortion to the lattice decrease with the distance away from a dislocation line. Look at here, Shabab. It's very important to understand when you just come close the part of dislocation, you see the more distortion. Distortion. Do you know distortion? I think in Arabic, the word in Arabic distortion. This is anyone can answer, please. Give me a word just equivalent to the word distortion.
تشوه.
أيوة تشوه. Yes, this word. If you look at here, Shabab, again, just when you come close the dislocation line, you see more distortion there. But if you go away from this line, you feel that the distortion will be reduced. This is what's written here. Okay, come to the most important part to understand for the dislocation, to understand the Berger vector. It's called B, Berger vector P. This is a measure of lattice distortion. By the way, there is some example or problem we're supposed to solve it. I just omit this part from the calculation, okay? Just to understand the idea. It's called Berger vectors. let me go ahead. I will explain it here. Look at the shabab. If, for example, this is a crystal structure, and we start from here, let us go ahead and count with me, please. There is 1 unit, second, third, fourth, right, shabab? Is that clear? If you can, 4. If you go from the other side, that one count 1, 2, 3, 4. This is 4. This is correct. But come to the up and bottom. Okay, count 1, 2, 3, 4, 5. We have 5 here. Count from the bottom 1, 2, 3, 4. We have 4 here. So this is not what perfect crystal. I think in order to make it as a perfect, this means all the missing lines supposed to be there. You have to add 1 here. صح يا شباب? To make balance between them. Okay, this one, if you need to add 1 here, we added here as حاجة اسمها Berger vector to make balance between this arrangement. This is called Berger vector. If the Berger vector is found, this means this dislocation is there. Okay, dislocation, missing lines of atoms is here. As you've seen it here, شباب, is very clear. Inverted T, حرف T معلومة. Okay, is that clear, شباب? Let me explain it again. You will understand. For edge dislocation, as I mentioned before, if you are talking about the point defects, the one we studied last week, we have missing of atoms. This missing of atoms called vacancy, and we have interstitial and substitutional solid solution, both of them point defects. It already explained in detail. Today, I'm going to explain linear defects. The line of atoms missing. Line of atoms are missing. Okay, this is we have 3 types. حاجة اسمها edge, a screw, and mix it between them. The edge is very simple. We have inverted T, as you've seen it here, and we can count what is the distortion by حاجة اسمها Berger vector. Okay, let me go ahead. If you look at here again as well, edge dislocation, we have Berger vector B supposed to be 0. There is no defects here. If you go from here up, count it. We count it as 4. We count that one as 5. We count this 4, and this is 5. This is perfect. There is no Berger vector here. Berger vector is supposed to be 0, right? But if you go to no net vector in the perfect crystal. But if you go here, the missing line of atoms or dislocation is there. You count it in this direction, you will find it. Like I give it to you. You count it. This is 5, for example, and this is 4, and this is 4. So it's missing 1 here. The one who just make balance between them is called Berger vector, and we have here inverted T. Is that clear, Shabab? I think it's clear. Yeah, you understand it. Okay, Shabab. Move. Shabab, should I move? This is called edge dislocation. Come to the screw dislocation. This screw dislocation, you can see it definitely in 2D is harder to visualize. Okay, that is why you have to see it in some of the 3D images. Let me go ahead. I will show it to you. It's harder to visualize than the edge dislocation. You can see it only in a 3D graph. I will look at here. Do you see this part like the screw? This is come in this direction, and this is in this direction. It's coming, making some of the distortion here. Okay, شباب, عرفوا or no? يا شباب, عرفوا? Yeah.
Yes.
Connecting like, yes, this connecting like a screw, as you've seen it here. It's very important to understand here the line of dislocation and Berger vector. I need because it's very important student understand this part. A screw dislocation, as you've seen it here, is a rampant step in crystal planes. تلاقي رامب حتى نطوق كده ظهر في الماتيريال. Okay, حاجه اسمها rampant step. If you look at here, شباب, this is a Berger vector. This is the value of the Berger vector B, and this is the line of dislocation. This is the line of dislocation, and this is Berger vector V. I need answer of any of the students. What's the relation between Berger vector and line of dislocation? What do you see here? And it's in the screw dislocation.
The Berger vector complete the deformation.
No, this is the definition of the Berger vector. Now what I'm asking you is the relation between the line of dislocation, this line, and the Berger vector itself. What is the relation between them? What do you see? What do you see يا شباب؟ Is parallel
Berger vector, I think,
Perpendicular.
is parallel to each other, right?
Yes.
Yes.
شباب, is parallel. This is important to me. This is important to me. In a screw dislocation, the Berger vector is always parallel to the line of dislocation. دائما وابدا parallel. Let me go ahead and will explain both of them again. Berger vector, which defines the direction of the atom displacement from the screw dislocations and parallel to the line of the direction. Five. What do you think the relation between Berger vectors and as the line of dislocation in edge dislocation, not a screw dislocation? Anyone can answer, شباب? Huh? شباب, anyone can answer? شباب. Yeah, شباب. طيب, let me come back. I will show it to you. Look at here, يا شباب. Just I give it to you again. Look at here, يا شباب. This is a line of dislocation. It's perpendicular to the page, as you've seen it here. And this is a vector, Berger vector. This is a Berger vector, and line of dislocation is perpendicular to the page. What's the relation between the Berger vector and line of dislocation? Hey, شباب. In edge dislocation, what is the relation? The relation is perpendicular. If I come to one conclusion here, Okay, what is here? In edge dislocation, Berger vector, شباب, are you following or not, شباب?
Yes, doctor.
Yeah, شباب,
yes.
okay. Berger vector, هو B. In edge, this perpendicular to line of dislocation. While and screw dislocation location, what is here? Berger vector B is parallel to line of dislocation. This is a conclusion I get it from here. Okay, let me move forward. As you see in it here, شباب, Berger vector, which defines the direction of the atom displacement from the screw dislocation, is parallel to the line of dislocation. As you see in it here, this is a line of dislocation, that one, and this is a Berger vector. If you look at here, it's parallel to each other. Okay, linear defects screw dislocation again. Let me go ahead. I'm talking about the two extreme. If you look at here, this is a Berger vector and the line of dislocation here, perpendicular to the page. Okay, because the linear vector is always perpendicular to the dislocation line, but in a screw dislocation is parallel to a line of dislocation. I think it's clear. Okay, شباب, it's clear. Come to the conclusion here, mixed dislocation. If you look at the dislocation, there is many dislocation inside the material and has very important part of the deformation of the material. I will explain it today. But if you look at here, the majority of dislocation inside the material is not edge, or maybe is not a screw. It's a mix between them. Okay, it's not a pure edge or pure screw. It's a mix between them. Let me go ahead. The exact structure of dislocation in real crystal is usually more complicated than one as shown, اللي هو ايه؟ الedge and the screw. There's a mix between them. Okay, we come to the conclusion, شباب. If you look at here, is this part, حد يقول لي what is the type of the dislocation here? حد يقول لي. شباب, this is a linear defect. A screw dislocation. طب look at this part. شايفين this part? Seen it or not?
Yes.
Yeah, what is the type of dislocation here?
The inverted T, which is
اللي هو edge.
edge. Yes.
يبقى here screw and this is edge. Excellent. But sometimes we will see mixed between them. But one important thing you have to know. What is this? The line of dislocation comes from the this part اللي هو edge screw dislocation and pass through to the edge dislocation is the same line. This means I have one conclusion here. If I have the mixed between the line and the screw, the line has a Berger vector B and the screw has a Berger vector B. Because they are connected to each other, it has one Berger vector. If the length of the Berger vector for the mixed one connected edge and the screw supposed to be the same. This is the conclusion you have to know. Okay, edge and the screw dislocation are just extreme from the of the possible thing. Just only give me a while. I have just answered. This is important. What? شباب, are you following? Just 1 minute.
Take your time.
Take your time.
Okay, Shoaib. Sorry for that one. Let me just go ahead. Shoaib, are you hearing me?
Yes.
Okay, you see the screen or not? You see the screen, right?
Yes.
Okay. Look at here, Shoaib. Again, as I told you, I need from the student to understand the course and to get conclusion what I'm saying right now. We know the line linear defects is called dislocation. We have 3 types. Edge dislocation with inverted T, and the screw dislocation. This is like a bump slip in the structure itself. As we know, the line of dislocation is perpendicular to the Berger vector in edge dislocation and parallel for the screw dislocation. Second, this is the Berger vector has a length, right? If there is a mix between this link between the edge and the screw, you have to know has the same Berger vector. This is a conclusion I need the student to understand. Okay, most dislocation has a mixed edge and the screw together. Okay, as you've seen it here, is like in the part of the edge dislocation is like the lines compress each other. تلاقي الحتة دي كأنها compressed, is making a compression here. But here, as distortion from the screw dislocation. As you've seen it here, the same line. If the same line mixed between the 2 types of the dislocation, we expect the Berger vector is the same. Okay? Dislocations with both edge and the screw dislocation as here, this is the conclusion, Shabab. No matter how complex and messy dislocation lines structures might seem, it can have a single Berger vector quantifying it. Is that clear, Shabab? I think this point is clear, right? Shabab?
Yes.
Okay. Right. I come to the one of the example I explained it before, and I'm asking you, if you remember, I already asked you about it, and point defects, right? Where do dislocation come from? What is the cause of dislocation? It's like, what is the cause of the point defects? What do you think? Shabab, what do you think?
The heat treatment.
Yes, heat treatment, excellent. Heat treatment, it can under the category of thermal stresses. You can get any thermal heat treatment stresses happen to the material. We expect dislocation, right? What is else, Shabab?
Cooling treatment.
Yes, all the heat treatment is thermal stresses. What else, Ishmael? What do you think? You can find. I need to ask you some question again. If I'm asking you,
I think the solid mixing, if it's mixed,
what is mixed?
the element is mixed with other,
Drawing
elements.
Do you mean do you mean when I just try to form the material, you mix a different material together, you can get this dislocation? Yes. Okay. If I'm asking you one question right now, do you expect to have a material without dislocation?
No,
No.
because there is no perfect
Okay.
pure material.
The second question, do you have a material with no vacancy? Of course not.
No.
يبقى here we can get a conclusion. We have many things that can cause the dislocation. Let me go ahead. I will give it to you. Most crystalline material, especially metals, have dislocation in their as form state. Do you know, like the one student answering me right now, maybe he answered, but is indirect. When you form the material itself, you just prepare the elements and mix it together. This is during mixing and something happen like this, you can expect the dislocation. Okay. The second case, come to the mechanical stress. When you make حاجة اسمها forming process. What is the forming process? As I told you, this part will be explained in detail in the course of manufacturing. If you need to if you have a diameter, for example, if you have a sheet like this, if you have a sheet metals like this with big thickness T, right? And I put it between a two roller, okay? This is thickness, I put it between two roller, as you seen it here. This is a simple example, but just I need the student to understand. You get a thickness, smaller like this. Okay, Shabab? You get it, Shabab?
Yes.
You get this part or not? This is called forming. You reduce the length by two roller, like you see it. If you do forming process to the material like this, you make a plastic deformation. When you squeeze the material like this, you expect a dislocation is formed. Okay? But this is called mechanical stresses. The second part, thermal stress, all of you understand, like heat treatment or heating, cooling, and something like this. You expect the dislocation. And finally, of course, solidification. On the material it is in liquid phase. This is liquid. I'm not. When you make a heat treatment, by the way, Shabab, you don't reach to the liquid. Still, the material when you're heating, for example, the steel we are working in the lab, still in the solid phase. But if you have a material like a liquid and try to solidify, to let it cooling down to get a solid. During solidification processes, you expect a dislocation. You will have at least three methods or three idea to get a dislocation. Okay, come to how to quantify the dislocation. If you remember, Shabab, the last week I'm explaining the number of the vacancy. We get some problem and we solve maybe 4 or 5 problems together to get the number of the vacancy inside the material, right or not? Yes, we have equation and we find the number of the vacancy. So we quantify how much vacancy inside the material with the equation, right? Now, if I'm asking you how to quantify the dislocation, يعني ازاي نقول الماتيريال دي, this material has more dislocation than the other material. Is that clear, Shabab? You understand my point or not? So in order to quantify, to calculate how much this dislocation inside the material, حاجة اسمها dislocation dynasty. Okay, Shabab? In order to quantify that one, we can use حاجة اسمها dislocation dynasty. Okay. What is the dislocation dynasty? This is the total dislocation length per volume. يعني مثلا لو انا اخذت cubic meter or cubic millimeter or cubic whatever from the material and say how much dislocation is counted there, you can say this is the dislocation dynasty. Or the number of the dislocations that intercept unit area. Again, Ashar, in order to understand this one, let me go back here. If I take, for example, a unit volume of the material, let me say 1 millimeter. 1 millimeter. Are you following يا شباب or not? شباب.
Yes.
If I take this volume, for example, and count many dislocations there, count number of dislocations. You can say this is, for example, 10 power 3 dislocation per millimeter cube. This is a density. يبقى الدنسيتي الموجوده في الماتيريال دي. For example, this is a demonstration or demonstrative example. Okay, I have 1,000 dislocation per millimeter cube in this material. If I have material A, for example, material A and material B, this is have 1 power 4 dislocation per millimeter cube, and this one has 10.5 dislocation per millimeter cube. Which one from A or B has more dislocation? Or has more impurity inside? Or has more defects inside? What do you think? A or B? B, because the number of dislocation inside is bigger. This is the first case. The second case, you can quantify. This is the density in there. If you, for example, this is 1 millimeter cube, 1 millimeter per 1 millimeter, and count how much or how many of the dislocation passing through this area. But for example, I say A, I have, for example, 1 or 500 dislocation passing through this area per millimeter square. And the second one, 800 dislocation passing through millimeter square. That is why I can say this is has more dislocation than the B1. Is that clear, Shabab? You get the point? Shabab, clear?
Yes, yes.
Okay, so the dislocation density, we can calculate it in that way. Either the total length, the dislocation length, we count the total length of the dislocation per unit volume, or the number of the dislocations that intercept with the area of the random section. Let me go ahead here. I give you some example. Why I'm giving you this example? To get an idea, to get a conclusion, okay? I'm not asking the student just to memorize this number, but you get a conclusion from this one. Look at here, Shubha. For carefully solidified metals, crystal, and I عملت a solidification. Metal is in the liquid, and just make it just cooling down to reach the solid case. Okay, dislocation density is around كام يا شباب؟ 1000 per millimeter square. يبقى واختار السكند case. Okay. For heavily deformed، لو الماتيريال عملنا لها deformation شديد، metals dislocation density can be 10 power 9 to 10 power 10 per millimeter square. Okay, are you following يا شباب or not? شباب,
Yes,
are you following or not? Okay. For heat treated metal، لو أنا بتكلم على heat treated metal، dislocation density can be the same here. Before I continue يا شباب, before I continue, this is my strategy. I'm always asking students to get conclusion. If you look at here, I can get conclusion from the three. If you make a careful solidification of the material, you expect less density or less dislocation than when you make a heat treatment or heavily deformed. Correct or false? Correct. If I don't memorize the number, but I get the conclusion between them. Is that clear, Shabab? Shabab, is that clear?
Yes, Doctor. Yes.
Okay, let me move forward. For ceramic material, I'm talking about the ceramics material, the dislocation density is around 10 power 2 to 10 power 4. Okay, Shabab, here I think the metal has more dislocation than the ceramics. Keep in mind this one, because I need this part when I'm asking, explaining the deformation of the metal. Okay, when I'm asking you or explain the deformation of the metal, you just pick up what I'm saying right now. The ceramics material is less than the metal, as you've seen it here. The number of the dislocations. Come for the silicon single crystal. I'm talking about single crystal. Silicon consisted of, this is used in electronics, by the way, used in integrated circuits and electronics application. You've seen it here, 0.121 per millimeter. It's very small amount, right يا شباب? But it's not zero. You get the point? You get the point or not? يبقى in single crystal, I am expecting in single crystal there is no much dislocation inside. When you talk about the polycrystal, you expect more dislocation. Is that clear يا شباب? Is that clear or not?
Yes, doctor.
Okay. Now I get conclusion from the dislocation, and we understand the line dislocate. The line defects is called dislocation. We have three types: edge and screw and mixed. Okay, I already explained everything. And second things, what is the cause of this dislocation? We explain it here, and we get conclusion how to quantify the dislocation using the per area or per volume. And we get some example to let you get the point. Dislocation example, Ishwat, I give you one image, just a real image of dislocation, by the way, Ishwat. If you see, this is, again, Ishwat, this is the lines, is not a grain. حدش يقول لي دي grain. عارفين grains أكيد يعني. All of you understand the grain from the optical microscope, but this is not optical microscope, okay? This image looks like the 3D, is not optical microscope. As you see it here, do you see it's like a thread? عارفين الثread اللي هو الخيط يا شباب? The same like that. This is this real dislocation, by the way. If you look at here, this is called the scale bar. The scale bar, this part is called 0.2 micrometer. يعني الحتة دي عبارة عن 0.2 micrometer. So this is lines is the dislocation. You get it, شباب? You get it or not? This is a transmission electron microscopes or micrograph of titanium alloys in which the dark line are dislocation. متكبرة كم مرة المagnification يا شباب? Do you see the magnification? You see it or not?
Yes, doctor.
شباب
Yes, doctor.
50,000 يعني الصورة دي متكبرة كام؟ 50,000 magnification. But in our lab, if you remember, we have different optical microscopes, and the biggest one that I'm always using to get the image and send it to you, this has 1,000 magnification. Here we have a transmission electron microscope can reach above 50,000 magnification, as you've seen it here. Okay, Shabab? Should I move? Yeah, Shabab?
Yes, doctor.
Okay.
Yes, please.
When a shear force is applied to a material, the dislocation moves. It's very important a student understand this one. This is a conclusion of the dislocation because it's a defect. Is this defect needed or not? I will explain it later on today. Yes, let me go ahead. Real material have a lots of dislocation. Okay, if you look at the single crystal is different from the polycrystal. Polycrystal, this means the dislocation is more. Okay, therefore the strength of the material depends on the force required to make the dislocation moves, in addition to bonding energy. As I explained before, in order to get the property of the material, you can go ahead by the bonding energy. The second thing, the structure itself, crystal structure. The third thing, if you are defect there, the defect affects the property of the material. Correct, totally correct. I will explain it here. Let me go ahead. Motion of the edge dislocation. Dislocation motion requires the successive bumping slip of the half plane of the atoms. Bonds across the slipping planes are broken and remade again in succession. If you see it here, the plastic deformation of the material of the most crystalline matter is by dislocation movement. I think you will understand all of these words or sentences when you see a graph. Let me go ahead, I will explain it one by one, because the student is supposed to understand and get conclusion from this one. Look at here. To deform any material to a plastic deformation, to slide atoms planes pass to each other. Let me go ahead, I will explain it. Do you see here, Ashraf? I think this is very clear, this image. Do you see it or not? شباب شايفين الجراف ده ولا لا؟
Yes, doctor.
Okay. If I'm talking about the line of atoms A second line is B, third line C and D. Okay, you seen it? I think it's clear, right, Shabab? Shabab, you seen it, right? When I apply force in this direction and another force in this direction, suppose all of this move in here and those suppose move in here, right, Shabab? اوكي يا شباب؟ اوكي look at here. There is no bond here. ما فيش bond في الحته اللي فيها dislocation. Right or not؟ ادي الانفيرتد تي يا شباب. عند ايه؟ صح يا شباب؟
Yes.
Yes.
This is AG dislocation. There is no bond to break here. What is happening when you apply the forces here in this direction? It's called shear force. Okay, it will break these atoms, break the bond here. Okay, it will break all of this bond. Okay, look at here, شباب. The second step. And when it break, this lines attach it to A, as you seen it here. شباب. And the dislocation, instead of coming to A, أصبحت فين يا شباب؟ عند B. Right يا شباب? You get it or not?
Yes.
So the dislocation moves in A. When you apply the force and the bond is breaking, this bond is breaking and immediately is attached to another place. The atoms moves. الatoms بتتحرك يا شباب عشان بس تبقوا عارفين. All this line is moved. So the second step, A was the dislocation is there. Now there is no dislocation at A. The dislocation moved to B. When you just apply the force again, the movement will be go from B to C and finally to D. So the material will be motion, in motion here. Okay, you get the point, شباب. Look at here. I think it's very clear from here. If you know the caterpillar, عارفين الكاتربيلر اللي هي دي الشكل ده. عارفين الحشرة اللي هي الكاتربيلر. If you seen it here. If you seen it here, when it move بتلاقي الحركة دي بتتحرك لفوق. كأنها هي dislocation. Right? The same analogy between it. كأنها dislocation. When it move again, this pumping, as you seen it here, it move it here. يعني دي بتنزل دي بتطلع. Right يا شباب؟ يبقى dislocation اتحركت. You get the point يا شباب؟ شباب is that clear or not؟ يا شباب.
It is clear.
شباب
The atoms move when you
yes.
exert an external force.
Force. The external force makes the dislocation move. Okay? You get the point يا شباب? This is the
Yes.
conclusion here. I have one question before I move. I have one question to all of you. If I'm asking you now, imagine I have a material like this and there is no dislocation. And you apply a shear force. Do you expect the material itself has more strength? هيحصل لها deformation ولا لا؟ Is the deformation occur when there is no dislocation?
No.
No, the deformation is depending on the vacancy and dislocation. In order to make the material moves, يعني for example, if you make, for example, you bring a part of the steel and try to stretch it, it will be deformed, right يا شباب؟ مش هيحصل لها deformation? Yes, and not break, by the way. هيحصل لها deformation and not break. This deformation happen only if there is a dislocation there. But if there is no dislocation, when you just deform it a little bit with the force, it will be break. هيحصل لها break without deformation. You get the point or not يا شباب؟ يا شباب, you get the point or not? يبقى here is very important to understand dislocation is very important for the deformation of the material. Okay, because it making a slipping, as you seen it here. I explained it in that graph. It is needed to move the atoms from its place from one place to the other. If there is no dislocation, the deformation is very difficult, and when it happens, the material is break. It's a lot break without deformation. Okay, I will come back because I need to say the conclusion here into that one. Shabab, are you following? Shabab?
Yes, doctor.
Are you following? I need that one. Where is this one? This one. It's very important here. If I'm talking about the metals, as you've seen it here, the metal has more dislocation, is 10 power 10 or 10 power 9. If you are talking about the ceramics material, for example, where is the ceramics material? كام يا شباب؟ ها؟ 10 power 2 and 10 power كام؟ 4. This is small compared to the metal. That is why when you need to deform the metal, the metal can deform it very easily. بيحصل له stretch before breaking. But if you need to deform the ceramics because it has low dislocation, you expect it's very hard. Okay, it will make a resistance to the force and break very easily. Do you know the ceramics material يا شباب؟ عارفين السيراميكس سيراميك يا شباب؟ You know it, right?
Yes, Dr. Yes.
You know the ceramics, okay,
Yes.
and you know the metal. For example, aluminium. When you stretch the aluminium, it will be stretched, deformed with you, right? But when you try to stretch the ceramics, it will be break, right يا شباب؟ مش هيكسر, right or not?
Yes, yes.
That is why, because the ceramics has low dislocation inside, it cannot deform it very easily like the metal. Metal has more dislocation. It can move, the atoms can move easily, but in ceramic is not. I think the conclusion is given here. Let me move forward. I already explained the motion of the dislocations, and we give analogy with the caterpillar. You understand it? Okay. Come to the now you understand the planar the edge defects, right, يا شباب? You understand or not?
Yes, the linear.
Correct.
Yes.
Okay. Okay. Let me. We have three types as I explained it. This we have edge and screw and mix it. We understand the deformation and the dynasty of the dislocation. Come to the planar defects. Okay. The planar defects could be free surface in crystal. This is the first one. I will explain it. And grain boundary, I think I already explained it many times. I will explain it today again. And we have a third case in under the category of planar defects is called stack and folds. Okay. And finally, حاجة اسمها twinning. Okay. Let me explain one by one. So a free surface يا شباب. Look at here يا شباب. Do you see that one? If I have some atoms like this, okay, what do you think is the bond between the atoms? I will pick up some atoms and you answer me, right, Ishaq? I will pick up some atoms and you answer me, please. If you look at here, Ishaq, if I pick, this is atoms A, and I will have atoms B and atom C. Look at atom A. This is in the center. It's bonded in all directions with the atoms, right or not? Correct. Right or not? So if you look at here, the atoms inside the material is connected from atoms from all directions. We expect the bond in all directions. But look at the B in the surface. Has a bond with the atoms in the same surface, but in the upper surface there is no material there. Maybe the atmosphere. You expect here the bond at B is the same like A or different?
Different.
Maybe different.
Different, excellent. At C as well. C has bonded, has touching the surface and touching another atom. I expect the different as well, right? So I come to the conclusion here. Surface atom has unsatisfied atom bond. Correct. Because it is bonded with the atoms beneath it. Okay, but the upper part is not connected. And higher energy than the bulk atoms. Okay, as we can get closer to the free surface, a material, the upper surface, the boundary between the object and the atmosphere become more distorted. بيحصل لها distortion في الماتيريال. Okay, يبقى الديستورشن بيحصل فين يا شباب؟ at the surface. Okay, why يا شباب؟ Because the atoms itself in the surface is bonded with the atom beneath it in the material, but it has a contact with another surface at the top, right? That is why more distortion it will be there. Okay, this is called سميها يا شباب free surface in crystal. يبقى the first defect in planar defect حاجة اسمها free surface. I think it's clear right now. Let me move to the second one. This has a regular pattern surface, and that one has more distortion. Come to the planar defects grain boundary. I think all of you understand the grain boundary, right? When I already explained the solidification, and when the grain is formed, between the grains there is a lines or curves, that lines or curves, we said a grain boundary. Okay, and we get many of example over there. Okay, grain boundary dislocations G, B, D, linear defects within the boundary. هتلاقي زي lines كده مع boundary as you seen it here. Okay, boundary between the crystal we understand, have the change in crystal orientation. I already explained this part before. Okay, شباب. Embed the dislocation motion. Okay, شباب. I need from the student to understand that part. Let me go outside. شباب, are you following or not? يا شباب.
Yes, yes, دكتور.
Yes.
Imagine يا شباب, imagine we have grains like this. Okay. We have a material with grain like this. Okay. If I apply force in this direction and force of this direction, مش الماتيريال فيها dislocation؟ صح يا شباب؟ مش كل جرين فيها dislocation؟ يا شباب.
Yes, yes, yes.
شباب, yes, okay. What will be happen? As I explained before, if there is a dislocation here, as you see here, inverted T, when you apply the force, if there is a dislocation, the dislocation move. صح يا شباب؟ Dislocation moves to make a deformation. عشان يحصل deformation في الماتيريال يبقى لازم الديسلوكيشن يحصل لها يا شباب moves. Is that clear يا شباب? You understand this point? I think from the
Yes.
previous example. Let me come to the grain and the dislocation. Grains and dislocation. What's the relation between them? When you apply the force, the force, المفروض الديسلوكيشن بتتحرك جوه الجرين. لكن تيجي عند الجرين باوندري كانه عائق ليها يا شباب. يبقى this is obstacle. Okay? يبقى here I can get a conclusion. Grain boundary embed يعني ايه يا شباب؟ بتعيق the movement of dislocation during deformation, and as a result it made material more strength. يبقى إذا the dislocation here makes the material more strength. Explain how? Because the deformation of the material can be classified under the movement of the dislocation. If you embed or stop the dislocation from movement, you make the material strength. You get the point يا شباب? And here we understand the grain boundary is to stop the movement of the dislocation, not to stop embed, بتعيق حركة movement of the dislocation. And that is why the deformation will be less. The material gets strength. Is that clear يا شباب? This point is very important to understand here. But the grains embed the dislocation motion, and that is why it can increase the strength of the material, the grains itself. Okay, let me move forward. Is that clear يا شباب?
Yes, دكتور.
يا شباب. Okay, let me move forward. طبعا it's produced by solidification. I already explained this part before. Okay يا شباب. Again, if you remember, all of you study in the lab when you do the heat treatment or as received steel, you prepare your sample, cutting, mounting, grinding, polishing, and etching, and seeing it under the microscope. You see the grain, right يا شباب? Is that clear or not? يا شباب.
Yes.
You see all of you see the grain in reality. You seen it under the microscope. I think it's all the lab you did based on the grains. You seen it there. Okay. How to calculate the number of the grain? And if for example, Shabab, it's very important to understand because I have question here. I will explain it at the end of this lecture. If I have time, I can finish it today. Okay. If I have grain like this, and I have another image, everybody A, image A, and image B, have grain like this. Okay. And I'm asking you, can you compare the two images from the first instant? I need answer. Whose has more grain than the others? حد يقول لي.
The A.
ايه
ثلاثة.
A or B?
A.
Of
A
course,
has
from
more.
the first from the first instant, a student can say A, but it could be wrong. Could be wrong. One of the students may say, that, Doctor, you are saying a puzzle for us. Of course, it's not a puzzle. I will clarify this one to you. In order to just make a comparison between two images as a grain, you have to find حاجة اسمها grain size number. You calculate the grain size number for this image and grain size number for that image. حاجة اسمها G. If G, A, greater than GB, you can say your answer is correct. But if GB is greater than GA, your answer is wrong. Is that clear, يا شباب? I have example in details. I will explain it to you. Let me move forward. Okay. Grain size, يا شباب. We have a standard, حاجة اسمها standard grain size number. Okay. In describing my microstructure, it's useful to have a simple index to grain size. It's very important here. The student just not go ahead and count the number of the grain and say this has more grain than the other. No, you have to find an index. This index is called grain size number. Okay, a frequently used parameter حاجة اسمها standard here, ASTM of the material, حاجة اسمها grain size number. We have two methods, by the way, to find G. Okay, two different methods. In order to find G, we have a big equation like this. Okay. Any image, you can find G for that image with using this equation. Okay, what is this equation? I give it to you here. N over A multiplied with 100 divided M all square equal to 2 power G minus 1. Okay? What is M is the magnifications. What is A is the actual area of the micrograph in inches square, by the way. It's very important to understand this. N is the number of the grain of the certain magnification per inch square. يبقى here N العدد of the grain here. Is this counted like 1, 2, 3 and so on? Of course not. We have a way to calculate that. And finally, you can find the grain size number. يبقى 3 parameter you have to count it here. 3 parameters. N, A, and M. Anyway, I have two different examples. I pick it up from the student work during the lab, and I will calculate it with you. The second method, a standard method again, to find the grain size number, you can use حاجة اسمها this part is called line methods. You have two methods here. Either here, in order to find G, grain size number, G. How to find it? حاجة اسمها area methods وحاجة تانية اسمها line methods. Okay? Both two different methods. You can find G. Let me go back. I will explain it here. So how to find G, or grain size number, using the line methods? You have to find L power, this is N multiplied with L, divided by the number of intercept multiplied with the M, magnification, and you get some lines like this. Okay, for example, 6 or 7. Maybe the best thing is the minimum to be 7 lines. I will explain it, by the way. Don't worry. Okay, and use this equation to find. Once you get L bar, you have to find G. Okay, with this equation. And log here with the base 10, by the way, not len. N is the number of the line. M is the magnification. L is the length of each line in millimeter, all the same. Okay, and G is the grain size number. Anyway, don't be fair about that one. We have some examples. We solve it together. You will see it very easy, by the way. You can train yourself, and it's very interesting, by the way. Okay, is that clear, Shwat? For the two cases, I have two examples. I will explain it to you. Should I move? So I will just wait for a while. I will explain example in details. Okay. Let me move. We're still in planar defects. We have the حاجة اسمها stack and fold. Stack and folds. حد يعرف the word folds? What does it mean in Arabic? Fold يعني عيوب يا شباب برضه. Okay. Stack and fold. Look at it. It's very simple to understand that one. Stacking faults or SFF are found in the metal when there is an interruption in the arrangement of the atom, A, B, C, and something like this. Let me explain it with the graph. I think is the best way to understand it. Look at here, Ashwar. If I have arrangement of the atoms like the hexagonal close bracket, we have atoms in arrangement, say C, for example, and 3 atoms here, A, and 2 atoms, for example, B, and again C. يبقى have here حد يقول لي كده الارينجمنت لو انا بدات from up to down, for example. A, 3 atoms. C, for example, this is 5 or 6 atoms. And B, 2 atoms and 3 atoms here. يبقى كان say A, C, B. صح يا شباب؟ Then A, C, B, and so on. مش ده order of the arrangement of the material. صح يا شباب؟ You get the point يا شباب؟ If I have atoms in certain arrangement, A, C, B, and for example, A is 3 atoms, C is for example, is 5 or 6 atoms, and B is 2 atoms. And it has the same sequence here. This is the correct arrangement. Look at here as well. Okay, look at here. We have A, then C, then B. This is correct. After A, B, C المفروض يبقى ايه؟ ها A صح يا شباب؟ وبعدين المفروض ايه؟ C. Is C here or B؟ في الكيس الثاني. What do you see؟ شباب الارينجمنت اهو. مش ده الكوريكت؟ A, C, B المفروض A, C, B and so on. He go from here, the first back, A, C, B, correct. But the second back start by A, then B, then A. Is this correct? شباب, is this correct? I need answer يا شباب.
Yes, I think.
You hear me? Is this correct in number 2? I think you don't get the point.
Yes, I believe it's correct.
لا, is not correct.
Yes.
بص يا شباب الارينجمنت اهو صحيح معايا. يبدا بايه؟ بعد كده ايه؟ سي، بعد كده بي، وبعدين يكمل تاني اهو A B ها A C B بنفس الدايركشن كده. فتعالى هنا A C B correct. بعد كده A B A. Is this the same sequence؟ No, it's not the same
It's
sequence.
not the same.
يبقى هنا حاجه ده بيسموه stack and fold. When the arrangement of the atom is not the same order, we say this is stack and fold, and this is called planar defect. Is that clear يا شباب؟ You get the point or not?
It's clear. Yeah.
I think it's clear. You understand? If we have the arrangement of the atom in certain way, and this arrangement is not repeated in the same way, we can say this is a fold, عيوب. And this is called planar defects. And what is the category of this planar defects? Is the stack and fold. Okay, let me move forward. The final one on the planar defects is called twinning. Sometimes the shabab we have plane of the material like the mirror. بتلاقي الماتيريال اتقسمت نصين زي الميرور كده. شايف؟ تلاقي الجنب اللي فوق زي الجنب اللي تحت as you seen it here. This is called twinning, and twinning may happen in the material many times. If you see a twinning like this inside the material, we expect this is a planar defects, and this is called twinning. Okay? ده بنسميها شباب twinning. A shear force that causes the atomic displacement such as the atoms on one side of the plane of twinning, الاتومز الموجوده في one side هتلاقيها زي الاتومز اللي الثانيه. Mirror the atoms of the other side. Okay? A reflection of the atom position. This is called twinning. If I'm asking you again, just a brief introduction, what is the planar defects there? The planar defects, we have many defects inside the material. It's called planar defects. The first one is called free surface in the crystal. We already Yeah, Shabab, you hearing me?
Yes,
Yes,
yes.
sir.
We cannot see the.
That's okay. I will make share. I don't know what is happening there, but sometimes it's don't respond.
البلاك بورد معلق يا دكتور يطلعني حتى احيانا ما ادري شو المشكله.
ما أنا هي دي المشكلة الكبيرة يعني. This is a big issue here. I don't know what happened. Let me come back here. I hope it works. Shabab, you hearing me? Yeah, Shabab.
Yes, yes, doctor.
Yes, doctor.
Now I think it's working now. Okay. Again, Shabab, just only as I told you from the beginning, I explained the planar defects. We have 4 categories. The first one is called free surface and crystal. The second one is called grain boundaries. The third one is called stack and falls. And finally, the twinning, as I explained it here. Okay? Okay, so come to the final part of this defects arising inside the metal. It's called bulk or volume defects. Okay, Shabab? And bulk and volume defects, I think most of you maybe captured by naked eye sometimes when you work in a lab. But let me explain it here. You may understand it. We have pores. عارفين pores؟ فتحات جوه الماتيريال. And sometimes when you cut your material and see it under a microscope, you see a big hole inside. This hole may be formed during the solidification. Are you following, شباب, or not? شباب, are you following? يا شباب.
Yeah, doctor.
Sometimes we have pores inside the material. These pores عارف زي فتحة جوه الماتيريال, okay? Or bubbles inside the material. During the solidification process, maybe the air trapped inside the material, and when the trapped is making pore inside the material, okay? This may happen, of course, as you seen it here. All this part is called pores inside the material, okay? This is called pores. The second case of the bulk is cracks, and this may happen in ceramics, by the way. Crack, عارفين الكراك يا شباب؟ شرخ جوه الماتيريال. This pores is not a crack, by the way. If you look at here, شايفين الجزء ده يا شباب؟ You seen it or not? شباب, you seen it or
Yes.
not?
Yes.
Okay, this is
Yes.
called cracks. Okay, and that crack, by the way, it happened many times in ceramics material and foreign inclusion. Sometimes you see a material and some of the impurities is added, or sometimes it's found inside the material. It making a volume defects. Okay, and this is, by the way, is very important for some of the electrical application. The coming week, this week number 7, I will talk about this kind of inclusions. Okay, Shwar? Is that clear, Shwab? Let me just make a brief to what we study of the defects arising in the metal in the 2 weeks, by the way. We have a point defects, a line defects, area defects, and a volume defects, okay? The number and the type of the defects can be varied and controlled, yes. If you remember there, we have some problem, we solve it together, we can find the number of the vacancy inside the material, and we solve some problem together. You calculate the number of the vacancy. Well, we can control by the temperature as well. Okay, defects affect the material property. Sure, this is definitely happen. As you seen it here, if there is no defects inside material, no vacancy, and no dislocation, how the material will be deformed? There is no deformation inside the material. It will be break very easily. But deformation happen when there is a dislocation. This is the defects, and we have a point defects inside. Okay. Can we control the strength of the material or deformation with this type of the defects? Yes. As I told you, grain boundary has a great effects in strengthening of the material because it stop or embed the dislocation movement, and that is why reduce the deformation inside the material. Defect may be desirable or undesirable. Sometimes العيوب دي في الماتيريالز احنا محتاجين العيوب دي في الماتيريال. If you need the material to be deformed, you need the dislocation, right? You get my point or not, Ashbab? If you need the material not break very easily, but it deformed, you need the defects inside. But sometimes here the fix inside the material is desired, other time maybe not. Okay, so dislocation may be good or bad depending on whether you need the plastic deformation or you need the deformation or not. Is that clear, Ashraf? You can stop me if you don't understand any point. Okay? Okay, Ashraf?
Yes.
I'll finish
Okay.
by today, but
Doctor,
I have some. Yeah, of course, I will answer you. Just give me 1 minute, I will say something and I will let you ask your question. Again, Shabab, I'll finish by today. We have some problem, we solve it together. After I finish, I will give you 5 minutes. I need to drink some water and we'll return back. We finish this 2 questions together. Okay? Your question, please.
Before you said you draw 2 picture for the grain.
Yes.
And I didn't understand how this grain could be greater than the other picture.
Okay, you will. Yes. Okay, that's. I will just clear your understanding after we go and solve the 2 examples together. You will understand my point. Okay. Just give me 5 minutes, Shabab. 5 minutes. Just I need to drink some water. Okay, and we'll come back and we will continue. Okay. By the way, you will understand in details. And when you finish, Shabab, I need from you just to go in a home and try to pick up any image like this and try to calculate it the same way I gave it to you and train yourself. Okay? Okay, Shabab?
Okay, Doctor.
Okay, 1 minute and I'm just 5 minutes. I will come back.